Welcome. Today we'll be discussing section 6.3. Topics include hyperbolas, standard position of hyperbolas, and the standard hyperbolic equation. For hyperbolas, we have the following definition of two distinct points, f and f prime. Again, that is distinct, meaning that they can't be the same point. We're going to have some real number, delta, which is less than the distance between these two distinct points. We'll then describe the set P as the set where the distance between any point on the set in F, or I should say a point in the set in F, minus the distance between the same point and F prime is equal to plus or minus delta. So where ellipses, we had the distance between f and f prime be smaller than delta, we have the other case here. Now, what does this describe? Well, if I draw two axes, and I'm going to call this one the major, this one the minor, and I'm going to have a foci here, F, and another foci here, F prime. And let's draw some hyperbola that looks like this. So what ends up happening is that, let me adjust this just slightly. There, so now it's halfway. So if I have my center, which is here, so I think of this Z as my center of X naught, Y naught. I then have my vertices, V and V prime. Those are the hyperbola on the major axis. And now I'm going to describe this distance here as A. I'm going to describe the distance to the center to the foci as C. So I'm using the same conventions as the previous video. I then, if I introduce the formula, C squared equals A squared plus B squared, that I can now make a box where the width of the box is the A and the height of the box is the B. And I'll call where the minor axis intersects this box with little m and little m prime. So those will be my minor points. So I've now described the same set of points as an ellipse with my foci, my vertices, my minor points, and my center. So this equation is useful because the C is essentially the foci distance. From the center. Again, kind of similar thing, except now we have a squared plus b squared instead of a squared minus b squared, as we had that in the ellipse case. We also have the width, and that we have delta is equal to 2a. So we'll end up having the same width, but we have a different way of calculating our C. So from this, we can define our standard position. Hyperbola standard position. we'll say that our hyperbola and we'll call it the script H. So this, let's label it as our H. With center Z x naught y naught as either. And we're going to run the same thing on if we're going to have a horizontal major, or we can rotate this entire thing 90 degrees, and now we have a vertical major. So in the first case, we have the horizontal major axis. And we'll now have the formula of x minus x naught squared all over a squared minus y naught squared all over b squared is equal to 1. And for the vertical counterpart, so vertical major axis, we're going to be left with x minus x naught squared all over b squared plus y minus y naught squared over a squared equals 1. And the last thing that I forgot to do is insert this negative out in front. So you can, so here we have a negative, and here we have a negative. You could write this as, put this up here. I think that'll be more clear. You could also write this, flip it, and write as subtraction. So have y minus y squared, or y minus y naught quantity squared divided by a squared minus this quantity of x minus x naught squared all over b squared. Either way, it's up to you. I like the consistency of keeping x's to the left, y's to the right. Now, notice that we have the same sort of restriction here, that a must be greater than b. Our major axis is still greater than our minor axis, and that's why we label them as such. So keep in mind that convention. Another way that you can think about it is that in this case, the b has the minus. We're subtracting that term. So what else can we say? We can say that the vertices for the horizontal are at x naught plus or minus a y naught. Our foci are at x naught plus or minus c y naught. Our minor points are at x naught y naught plus or minus b. And this is very similar to the ellipses, but we're going to include for this one is asymptotes at y minus y naught equals plus or minus b divided by a times x minus x naught. And what that would do is create these asymptotes. I drew my ellipse better. Sorry, my hyperbola better. These asymptotes, and if I drew this accurately, the corner of my boxes would intersect where those asymptotes would be. So if I wanted to adjust this to make it look right, my asymptotes would be there, and my hyperbola would look something like that. So if we draw it proportionally and everything correctly and precisely, you'll end up having the box with the diagonals of this box being your asymptote. Now, for the vertical, we're going to have the same sort of equations to find our vertices, which we're going to have x naught, y naught plus or minus a. Our foci be x naught, y naught plus or minus c. We'll have our minor points be x naught plus or minus b, y naught. And then finally, our asymptote and the equation of that will be y minus y naught is equal to plus or minus a over b x minus x naught. So the only significant difference between there is that we have the reciprocal of a and b between the two. However, if you think about it this way, the b is the vertical portion, a is the horizontal portion, in the sense of, since we have a major axis, this is our rise over our run. Here, we've changed the notation of a and b because now our a is our vertical distance between the vertices. So that's our rise, and our run is the distance between the minor points, but it's still a horizontal distance. So that might be a memory trick to help. So let's do an example. And in this example, we want to find the equation of a hyperbola with vertices v is -1, 1, and v prime of -1, 5. And we're going to have our focus f be -1, 7. So we can, again, similarly kind of write it out. We'll have -1, 1. We'll have a, let me write this a little better. V as -1, 1, that's here. Then we'll have a V of -1, 5, it's here. And then here's the F, -1, 7. And so we end up generating the vertical axis because we have our vertices here. So we can do the same process as before. So if we want to find the center with using the midpoint, we can just use the midpoint formula to find the midpoint here. alternative way to do that is we have our A and we have our delta. And we know that we could utilize that formula. However, I will use the midpoint as I used the other way in the previous video. So with the midpoint formula, we'll have that our center is equal to the point of -1 plus -1 divided by 2. And then our y coordinate is 1 plus 5 divided by 2. This leaves us with -2 divided by 2 is -1. And 6 divided by 2 is 3. And the -1 shouldn't be surprising because we're just going to stick to the same vertical line. But then the 3 is halfway in between these two. And so this is our center or our Z. So we have that now. Let's find our A. Well, our A is equal to the distance between our center, Z, and one of our vertices. So we can then write that as the square root of -1 minus -1 squared plus, and we'll have 3 squared minus, let's do 5 squared. Or sorry, 3 minus 5 squared. So here we zero out because -1 minus the -1 is 0. And here we have 3 minus 5, that is -2. -2 squared is 4. Square root of 4 is 2. C is equal to the distance between Z and our F. So our center and our foci, which then we can write this as the square root. Again, we'll have -1 minus a -1 squared plus 3 minus, what's our foci at? It was at 7. Square that. So now we have, again, 0 here. That cancels. 3 minus 7, that is -4. -4 squared is 16. Square is 16. And we'll take 4. No, it is just 4, not plus or minus 4, because we're thinking of a positive distance. So now we can calculate our B, which our B squared is equal, or we had C squared is equal to A squared plus B squared. So that means we have B squared is equal to C squared minus A squared. So let's plug in our C squared, which is 16, minus our A squared, which is 4. So that will leave us with 12. So this implies that we have B squared equals 12, take the square root, and we get B is equal to 2 square root 3. So now we have our center, we have our A, we have our B, and we can write down our formula. So we'll look and see that this is a vertical ellipse because this is our major axis. So let's write down that formula. We'll have negative x minus x naught squared all over b squared plus y minus y naught squared all over a squared equals 1. Plug in, no, just plug in chug. What is our x naught? Well, our x naught is -1. So we have a x minus a -1. So we're going to do x plus 1, y squared, put the negative on the outside, divided by b squared, which we have 2 square root 3, but what was our b squared? It was 12. So we'll just write 12 here, plus y minus y naught. What's our y naught? It's a 3. So we're going to have y minus 3 there. Square the term, divide it by a squared. A is 2, squared is 4. Set it equal to 1. And there is our hyperbola. So in very similar format, we're going to be able to do our standard hyperbolic equation. And it's going to look very similar as to when we did the standard elliptic equation. All we're going to have is a times x minus h squared plus c times y minus k squared equals m. So now this looks remarkably similar, except we're going to have that a c must not equal 0. That's the same. But a is of opposite sign of c. With that one change, when we start to establish rules for m, we now get something else. So if m equals 0, then the equation is two lines that intersect at the point HK at the center. What are those two lines? Those two lines are basically the asymptotes from before. So what happens if m does not equal 0? Then we have a hyperbola with if m is same sign as a, we get a horizontal major axis. M is opposite sign of A, and we get a vertical major axis. So you could also think of this as if M is the same sign as C, but in this case, we're just going to reference the same sort of entity. Now, the other way that you could think about this is if I'm the same sign as the term associated with whatever variable, that's the major axis. So if M has the same sign as A, then we have a horizontal because X controls the horizontal coordinate. And if M has the same sign as C, then we have a vertical major axis as Y controls the vertical component. So either way, this will be your check on learning is to write down the standard hyperbolic equation and include the information of if m equals 0, if m does not equal 0, and what is the result of it. But for now, we're going to do a equation. So let's do an example. And we're going to start off with the equation for x squared minus 9y squared plus 32x plus 18y plus 91 equals 0. We're going to follow the same exact steps as we did in the previous video. We're going to factor out 4 and have x squared plus, and we're going to have 8x plus some number minus 9 times y squared minus 2y plus some number is equal to negative 91. And I got the negative 91 because I just subtracted 91 to the other side. So now we want to do the same, complete the square process. So 8 divided by 2 is 4. 4 squared is 16. So there's a 16 here. But for me to add a 16 here, it had to be multiplied by 4. So that is the same as if I wanted to time or added 64 to this side. So that means I got to add 64 to the other side. Now, for this y, I have negative 2 divided by 2 is negative 1. Negative 1 squared is 1. But to add a 1 here, we have to times it by the outside coefficient, negative 9. So it's like that we actually subtracted 9 to this side. So we got to subtract 9 from the other side. Again, this is in the reference because I added 91 to the right side of the equation. If we want to, or subtracted 91 to the right side of the equation. If we want to keep this all on one side, just change the signs appropriately. So we can simplify, and we get 4 times x plus 4 quantity squared minus 9 times y minus 1 quantity squared is equal to, and we have 91 minus 9, that's negative 100, plus 64, that gets us negative 36. So now I can look at my reference. I have b, or I have my m not equal to 0. I have my, so I'm in this b type situation, and my m is negative, but my a is positive. So my m is of opposite sign of a. So that means I must have a vertical major axis. So let me write down that equation. I'll have a vertical major axis, which is x minus x naught squared all over b squared, attach the negative out front, and then we'll have plus, y minus y naught squared. I didn't need to actually do this. I want to obtain this sort of form. So let me just divide by negative 36. So let me obtain this form, but let's be, that's the target direction we're going. So when I divide by negative 36, divide by negative 36, divide by negative 36, divide by negative 36, and we have this 4 divided by 36. We can reduce that to 9. So I'm going to write x plus 4 squared, leave the negative upstairs, and divide it by 9, which is really just 3 squared. Plus, because I have a negative dividing a negative, so this will be now plus. 9 divided by 36 results in a 4. So we're going to have y minus 1 squared divided by 4, which is 2 squared, is equal to 1. Now again, I wrote it in terms of 3 squared, 4, and 2 squared because now we have our a, we have our b. We can write down all of our information over here. So our a is equal to 3, our b is equal to 2. So that means our c is equal to a squared plus b squared. Take the square root of it, so that's 9 plus 4, 13, square root. We'll have square root 13 for our c. So when it comes to our foci now, we'll write it as the following. Our vertices, which I'm just going to write as v. We're going to have x naught, which I should include that first. So let's do our center. Is our x naught, which is negative 4. Our y naught, which is 1. So our vertices v is our x naught, negative 4. And now our y is 1 plus or minus our a, which is our a, which is plus or minus 3. Our foci, f, is negative 4, 1, plus or minus our c, which is square root 13. And our minor is our x naught, so negative 4 plus or minus our b, which is 2. I'm sorry, here, this is 2, this is 3. My apologies on that. And then, yeah, because we have our terminologies switched. Yeah, just 3 and I'm wrong. This is 3, this is 2. And then what's wrong on my notes? Something's wrong. Let me double check real fast. Don't want to misspeak. Yes, okay, so we have this. So this is 1 plus or minus 3, and this is negative 4 plus or minus 2. And then we have just the same 1 for our y. And that is all of our points of interest. However, we still have our asymptotes. And so let's write them in down here. So our asymptotes we can write as y minus y naught, which is 1, is equal to plus or minus our a. So that's was 3 divided by our b, which is 2, times by x minus x naught, which is negative 4. Those are our asymptotes. And that's all the critical information. All right, with that concludes section 6.3. It also includes the topics for the Math 105 Trig course at Kansas State University. Thank you for watching the videos and have a great day.